This is KBYP's video on balanced modulators, leading to what's wrong with the balanced modulator in a Drake TR3. It's broken, and noticeably so, and has been since I've owned it, and kind of has been since day one, because Drake alludes to a problem with it in their manual. So 1960 was the advent of solid-state technology, or pretty close. That going into commercialization. And this balanced modulator has diodes, and they're not perfect. So, to troubleshoot something, we first must know how it works. This is the approximate schematic of the carrier balanced modulator amp, and sideband filter in the Drake TR3. On the left is a 9 MHz carrier oscillator, a tube and a crystal. Just an ordinary sine wave oscillator. That goes to a multi-term potentiometer, which is or can be replaced by the ordinary 450 series stock pot. It has a vernier, 3 big steel bearing balls. It's kind of a cheap and cheesy multi-term pot, but it seems to work okay. In between the two arms of the resistor is a diode bridge, RF on two sides of the bridge, ground, and the input or the balanced modulator upset, either AF signal or DC, on the other side. The two equal ends of the pot go to two equal ends of the primary of a transformer T14. When the carrier balance pot is adjusted correctly, there's exactly the same RF voltage, amplitude, frequency, and phase on both sides of this transformer primary here. So no current flows through the winding, so the transformer does nothing. There will be some electrostatic coupling, but that's fairly minor. Offset the potentiometer one way or the other. That puts unequal voltages, causes a current to flow, and causes the carrier to appear on the secondary side, amplified by the amplifier, but not passed by the filter, or not passed strongly, because the carrier should be pretty much outside the passband of the filter. The diode ring is two sets of two diodes, probably like 1N27s, very old diodes, small signal, low capacitance. But they are arranged such that if the upset voltage here goes positive, then essentially one side of that diode ring or the other will conduct a ground, either that side or that side, and essentially pull either this line or this line toward ground. That causes an imbalance similar to if the control were turned, but not quite the same. And that not only causes energy to appear and current to flow through the transformer primary, but also does what's called mixing, or a beat process. Modulation is really mixing. The term modulation implies generally in the sideband an audio frequency being imposed on an RF carrier, because we can't transmit audio. So next time you hear some poor uneducated fool in the air telling you that your audio sounds good, remind them that transmitters don't transmit audio, and they cannot hear your audio. The mixing process through a nonlinear device, and diodes are highly nonlinear, causes a mixing of two frequencies and generates an output of the carrier minus a frequency and the carrier plus a frequency. Then the purpose of the sideband filter is to block out the carrier in both cases, and also one or the other sidebands. in my TR3 and TR4 I've used one filter and two carriers. And I just realized getting this drawing ready for this video, I've got the carriers backwards. I'm using the higher frequency carrier for upper sideband and it should be lower, so I will probably have to reverse that. So the effect of the upset input being audio frequency into the diode ring causes both an imbalance on a transformer primary to allow current to flow and frequency mixing. That's a broadband transformer compared to 5 or 6 kC wide response from a transmitter. So that transformer is pretty flat. The switching, if you will, action of the ring will tend to put the positive going pulses of the modulation on one side and the negative on the other. Combine them together, you get the RF envelope with the modulation. The amplifier amplifies it. There are tuning capacitors, small ceramic pistons to null out the effects of the electrostatic coupling. And the output of that goes through the sideband filter. But Houston, there's a significant problem in the TR3, and that problem is illustrated by what a single tone test will produce from a sideband transmitter. The carrier here is mixed with, say, a 500 cycle AF signal down below, and we don't get a 500 cycle AF signal out, we get a carrier, because this is not amplitude modulation. It's a sort of a frequency modulation, although it's not FM. The mixing results in the carrier being transferred through, and also a carrier up above and below in each sideband, which is offset 1 kHz from the carrier frequency. So out of the sideband filter comes that, basically a carrier envelope. We don't see a modulation pattern unless there's a varying multitude of frequencies. What's coming out of the TR3 looks more or less like the bottom drawing there. There's ripple on it. It appears to be writing on the crest. The 1958 Radio Amateur's Handbook suggests that that's because of a misalignment problem in a balanced modulator, although that text does not refer to a crystal filter. It refers to a phasing system. With a two-tone output, there should be a more or less sine wave looking output. But what's happening in the TR3 is that the rising edge here is grossly distorted. It comes up and it's kneed in, and there's clipping up here. And that is due to something called carrier leakage. No matter where the carrier bounce pod is, it can be set to a minimum. There's still carrier leaking through. And incidentally, there's also a small 35 mV DC voltage on the balanced modulator upset line. Since the TR3 and TR4 are plagued with the brown boards that have the rivets for connecting components, it's plagued with DC leakage across those from high voltage sources. I isolated all the wiring, the other circuits, not caused externally. The DC voltage is being created in the balanced modulator ring. And that's happening when the carrier is the same amplitude on top and bottom. I verified that with the scope. Therefore, since an upset in the input voltage, see, the AF DC line can be upset by a DC voltage also. And that's what's done to pass a carrier in CW and AM. But that results in an imbalance in the RF voltages on top and bottom. Conversely, it should be that a difference in the voltages top and bottom might generate a DC voltage. Well, the voltages are the same. I proved it with a scope. So that implies that the balanced modulator diode or diodes are defective or more likely not matched correctly. This was made in 1962 or 63. Diodes were in their infancy. It's a bit of a trick to make very closely matched diodes for a modulator. We can get them nowadays very precisely matched. But the 1N27 type of diode is probably 35 picofarad reverse biased. Diodes have a varying capacitance when they're reverse biased by different currents or voltages. They'll have different capacitances when they're forward biased. Very, very complex devices. So it's very likely that there's an imbalance in one of the diodes. And interestingly enough, the DC upset, that spurious little voltage of 35 millivolts, exists across two of the diodes in that bridge. So the diodes don't measure with a diode test to be shorted. They're about 0.235 forward drop. But when operated dynamically, there's probably a difference in capacitance, and that's causing a problem. This was an original problem. Drake alludes to it in the alignment procedures that say adjust the carrier balance as best you can. It doesn't say adjust it to eliminate all the carrier. I've never been able to get rid of it all. So that implies buying either modern matched diodes or buying an IC with a balanced modulator ring inside, which is best, because those will be precisely matched. Here's a Drake TR3 schematic with V16, C6GX6, carrier generator and demodulator, the carrier balance pot 200 ohms, the equal connection through 470 ohms to the transformer legs, and the diode ring. And T14 is a balanced modulator transformer, V15 amp, coupling transformer, and sideband filter. Here's the test equipment setup. TR3 ready to transmit into a dummy load PL259 RF input. The output is a attenuated port down to 6 milliwatts through resisted divider, 50 ohm output. That goes into channel 1 of the scope. Channel 2 of the scope goes to the highfalutin signal generator. That's the modulation source. We'll start off with a 500 cycle signal. And that also goes over to the TR3 microphone input with a switch, push-to-talk switch. This is a single tone input, so generate a carrier out. Can't get a modulation waveform without a two-tone. This generator doesn't generate two-tone that I know of. It does have a harmonic function, which I can turn on, and it'll generate at the same time a 500 and a 1000 hertz tone. And that will give a tone output, a sine output from the transmitter in channel 1. This is with the transmitter on. As you can see, there's a carrier. If I adjust the carrier balance pot, it won't go away. And there's the root problem. Close but not good enough. And this, unfortunately, is the output from the TR3 sideband transmitter with a single tone input. It should be a carrier. It's modulated. Turning the carrier balance control does that. But right about there is a minimum carrier. See the severe distortion either side. Changing the carrier frequency down does this. Changing it up greatly diminishes the output. Taking the frequency up so it goes through the pass band of the filter system does that, but it should just be a carrier. Two-tone test, gross distortion, gross distortion, gross distortion everywhere we go. Changing the frequency of the carrier does that. Too low, it does that. So it's just an ugly mess all the way around. That's about as good as it gets with the stock TR3.